Good afternoon, everyone. Welcome to today's webinar session. And just a reminder that this session is being recorded and the recording might be shared later through our website. So just a quick reminder here.
Tong, I think we can start. Would you like to give a short introduction? Thank you. Yeah.
Of course. Is my screen shared okay?
Yeah, looks brilliant. Thank you.
Yeah, brilliant. Let's get started. Okay. Good afternoon, everyone. Welcome to today's webinar. The topic is integration of energy storage and hydrogen infrastructures in future energy systems. Just a reminder before the session, this webinar is being recorded and the recording will be shared later through our website. Today, we have two excellent speakers, Professor Seamus Garvey, Professor of Dynamics from University of Nottingham, and Dr. Hossein Ameli, Research Fellow from Imperial College London. And they are going to give two brilliant presentations on this topic. The agenda for today's session will be me and Chun will give a brief introduction of both hubs because we are co-organizing this webinar. And then we will have Professor Seamus giving the first presentation and Dr. Hossein giving the second presentation. And we will have a 10 minutes Q&A session later on. So shall we start with your introduction, Chun?
Yeah, with pleasure. So I'm just going to share my screen. Just bear with me.
Yeah, of course.
Let me see. So please slide. Hopefully this is working out. Yeah. Can you see my screen?
Yeah.
Okay, then brilliant. Yeah, so I'm just going to do this very quickly. So again, this is a first webinar series, which is co-organized by the Supergen Energy Storage Networks hub, and also with the HI-ACT hub, which Dr Zhang is a committee member of. So I'm just going to give a 2-minute presentation. So at the moment, I'm representing on behalf of Dr. Joshi. So she's currently a senior research fellow at University of Warwick and the secretary and the chair for the committee for the ECR, which is the Early Career Researcher Committee. So for this network, this is led by Professor Ding of University of Birmingham. So he is an expert in energy storage technologies, especially in pumped heat energy storage. So this network consists of over 19 academic members from over 12 institutions. So for example, even Nottingham University, where Professor Seamus Garvey is also an academic member of this network. So this equates to £1.2 million of funding, which is secured from EPSRC. And within the funding, it's been distributed to organize such as flexible funding to provide smaller portions of funds to support all kinds of activities like ECR research and travel funds, etc. So we have over 34 project partners to date, and we had a 48-month in duration, and the project or the network started around September 2019. So as part of interest, the network focuses on all kinds of energy storage available. So we're talking about electrochemical storage systems like batteries, electrical storages like supercapacitors, thermal energy storage included latent heat energy storage, mechanical energy storage, chemical energy storage, etc. So within the network, we look at the kinds of energy storage systems technically, So, for example, doing all kinds of analysis, but also integrating this kind of new technologies into the energy networks, the society usage, and also examining the social, economical, and policy as well when using this kind of energy storage systems. So the vision for the hub is to connect a diverse range of stakeholders across the energy community and to promote energy storage, research, and deployment. So again, as I mentioned, the ECR, the early career researcher, there is a dedicated funding available, opportunities to submit to the IET Smart Grid Journal, etc. So there's a lot of support given to ECRs. And if you happen to be an early career researcher, please do reach out to me or Dr. Joshi. So we would be very happy to discuss with you on supporting your research as an ECR member working on energy storage technologies. Sorry, I think I just skipped a slide. So this is the current committee member list. So again, we have a diverse range of members from industry and academia, from lecturers and assistant professors to senior researchers, etc. From Birmingham, Warwick, and from myself, I'm from Brunel in London. So again, do please feel free to approach us if there's any support we can provide. So thank you for this very short introduction about the committee of the Energy Storage Network Hub run by Supergen. Thank you, Tong.
Thank you very much, Chun.
So I'll just stop sharing my screen. Okay.
Yeah. So hi everyone. I'm Dr. Tong Zhang from Cardiff University. I'm the HI-ACT ECR Deputy Champion. So I'm here to give a quick introduction to HI-ACT. So HI-ACT, our full name is Hydrogen Integration for Accelerated Energy Transitions. Our hub is younger. We just launched our hub in last June with a 10 million direct investment from EPSRC for 5 years. We are a consortium of 11 universities representing all 4 nations, led by Professor Sarah Walker at University of Birmingham. The mission of our project is to deliver impactful research through co-creation with stakeholders, which delivers an evidence base for hydrogen integration in the future net zero energy transition. So what exactly we are doing now? Our vision is to ensure that hydrogen could be appropriately integrated in a future energy system through our holistic and multidisciplinary research. And we are now taking a comprehensive view across all aspects related to hydrogen integration across different technologies, sectors, places, and the whole energy system, just to understand how best to integrate hydrogen. And we are also exploring necessary trade-offs and technology coupling requirements that can allow the full potential of hydrogen as part of a decarbonized energy system to be realized. So our hub, we have 4 work packages. The first one is to develop a forward-thinking technology roadmaps of hydrogen and alternative liquid fuels. The second work package is to push the boundaries of whole energy system modeling methods, including improving the characterization of hydrogen and also exploring new and urgent perspectives in energy transition. The third work package is the coupling of information and data related to whole system planning and operation. And the fourth work package is to looking at the options and solutions from the social and political perspectives. We also have 6 themes related to EDI, ECR, UK policy, EU engagement, international activities, and industry activities. And here we have, here are our lovely group members. We have Director Sarah and work package leads David, Zhang, and Adam, and also other champions and co-eyes. We have a quite not small team, a group of ECR workers. Some of them are co-Is and others of us are working as PDRAs and newly joined PhD students. So compared with Energy Storage Network Plus, we might be a younger energy hub, and we are now establishing our ECR community in these several months. So please stay tuned for more information. And we also have our mailing list and different websites and social media accounts that you can follow us. And we are very open and welcome to any kind of inquiry, comments, and potential collaboration ideas. So that's all for our HI-ACT information. Thank you very much.
Yeah, thank you, Tong. I think, Seamus, if you can share your screen and for your presentation, maybe 20 minutes, that would be brilliant if we can put this together for that time.
We'll see how we go. Can you hear me all right?
Brilliant, fantastic. Thank you, Seamus. All over to you. Okay,
excellent. Thanks very much for the invitation. My name is Seamus Garvey. I'm a mechanical engineer at the University of Nottingham, deeply invested in energy storage. I'm giving this seminar at a very inconvenient time to me because this week I will be running, I'm the chairperson of UK Energy Storage Conference 2024, and I've put a little plug on the front page here for that. It's absolutely brilliant agenda set out now. I see lots of names in the attendee list that will actually be here later on this week as well. So looking forward to a very, very good conference later on this week. And let me say, I very much admire the joining together of energy storage and the HI-ACT program, because in fact, hydrogen predominantly, the purpose of hydrogen in almost everything is energy storage. And it just happens to be suited to the long durations of energy storage. We absolutely, in the Supergen program on Energy Storage Networks Plus, mostly is not about hydrogen, but we absolutely need to know what hydrogen can do in order that we understand what everything else has to do. And I think that's the way to look at it. Just a small correction on what Chun said initially. Supergen Energy Storage Networks was valid for 48 months, but we have not expired. We continue until September of this year, in fact, and the UK Energy Storage Conference is a key part. It's the sort of kingpin of the storage network activity. So I'm going to dive straight in. A very important report came out in September of last year. In fact, it came out on September the 8th of last year, which was the very same day that the UK got no bids for the offshore wind auctions of round 5. So it was a very good day for renewables and for the net zero mission in one respect, and a very bad day for exactly the same, or well, for the same mission, but a different reason, a very bad day on the very same day. The Royal Society report was led by Professor Sir Chris Llewellyn-Smith, a very distinguished individual, but it was supported by many also quite distinguished people. And I see Goran Strabak is on the call here. Goran was one of several people, experts in their field, who supported this very strongly and helped it to come to the right conclusions. I think they are the right conclusions. And the Royal Society report says, yes, we can run on all renewables, at least a net zero energy system, and we can in fact run it from all renewables. And if we do that, we put in about 30% too much generation. That is to say, in any one year, the wind turbines and the solar panels will approximately generate 30% more energy than we want to consume. And approximately 15% of that energy is just turned down. It's just discarded, because that is economically sensible to do that in the findings of the Royal Society report. And the other 15% are accounted for by losses associated with energy storage. And I put some numbers on here about the kinds of numbers of costs we can expect to have if we use only hydrogen stored primarily in caverns as the energy storage option for this. And it depends very strongly on how much we pay for the renewable energy generation itself. If we're only paying £35 per megawatt hour, then we can expect to have electricity delivered into the system at £57, you know, etc. You can read the table. The central assumption is about £40 per megawatt hour, or at least it was before September the 8th last year, which would be giving us a number probably around £65 per megawatt hour for electricity actually delivered into the system that people directly use. Let me pick out that this report envisions that we will have 44 days of storage. In other words, storage equivalent to 44 days worth of UK consumption. And UK consumption at the moment is just under 1 terawatt hour per day, but it's obviously going to go up as we electrify things like heat and transport. So it might it might easily get to 2 terawatt hours per day, and you could easily imagine us having 44 times 2 terawatt hours per day. And I'll make one more remark on this page before I page on. We have a requirement called strategic reserve that was agreed in the 1970s by countries who produced oil and fossil fuels, that countries should retain 90 days of strategic reserve. So I think the UK still has 90 days of strategic reserve of oil, and many countries do. So we're only in the same order with this proposal for hydrogen storage. We're only in the same order as the strategic reserve of long ago that was long agreed. But many people would consider this number to be astronomical and certainly very challenging. And I'm going to talk to you about is it mechanical engineering? It's thermodynamics. I suppose that's mechanical engineering. It's all engineering, really. I'm going to talk to you specifically about exergy. And if you don't already know it, you should. Energy does not matter. Exergy matters. And that's a provocative statement, but it's absolutely true. And I challenge anyone to challenge me about that. We don't care about energy. We're awash with energy. It's all around us everywhere. My room is warm. Outside is warm. I could cool that. I could take energy I could take terawatt hours of energy just out of Jubilee campus here in Nottingham, where I am. Energy is worthless. It's exergy that is worth something. And exergy is the ability to do work or to make electricity. And of course, you can move heat around if you have exergy, and you can move much more heat than the exergy that you consume in moving it. So mechanical work is pure exergy. When I cycle my bicycle into the university, I am expending exergy in order to do that. And I lose a lot of energy as well, but that's separate. The stuff that I really need in order to propel my bicycle is exergy. And electrical energy is pure exergy. And heat is not pure exergy. Heat is energy. And heat does contain some exergy, but it's not 1 joule of exergy for 1 joule of heat. It's usually a lot less than that. And heat at 100 degrees Celsius, for example, whilst it's all we need to make a cup of coffee, is not really worth very much exergy. 1 joule of that heat is probably only worth 20% of a joule of exergy, maybe 25% approximately. You use Carnot efficiency to convert from heat into work and vice versa. And here's an interesting thing. Coldness is negative energy because you take energy out of something to make it colder, and therefore it has less energy than it started off with, but it has positive exergy. You'll see where I'm going with this. Now, if you want to quantify how much exergy there is in a body of material, that is the exact same amount as the most mechanical work you could possibly get out of that material if you allowed it to come back into equilibrium with its environment. And when I say equilibrium, I mean equilibrium in every sense. So it's got to be in chemical equilibrium. And when we think about hydrogen, of course, hydrogen, we will store it as a pure gas, and then we will turn it back into its natural form, let's call it, in the environment, its lowest energy form in the environment, which is water. And so there's chemical exergy available in that hydrogen, combining it with oxygen that's all around us, so we don't have to pay for the oxygen, it's there already. We have chemical exergy that can come out of that as we allow the hydrogen to come back into equilibrium chemically with its environment. But there's also thermal exergy. So how hot is that hydrogen, or how cold is it, more relevantly? And there is pressure exergy. And when we think about chemical, usually what we do with chemical exergy to release it is we turn it into heat. And so really chemical exergy is a coded form of thermal exergy. It has to be turned into heat first. It doesn't have to be in fuel cells, arguably, but I'm going to say in engines. If you're burning hydrogen in an engine, what you're doing is you're turning that energy into heat energy, and then you're trying to extract some mechanical work out of it. So I put a star beside chemical exergy and thermal exergy because in both cases, there's a theoretical maximum about how much you can suck out of that. And then there's a practical maximum. And the practical maximum is much lower than the theoretical one. And the practical maximum is limited by the materials we have. We don't have materials that can stand 1,000 degrees, for example, and carry a lot of stress. They don't exist. There are no materials that can carry a lot of stress. There are no affordable materials that can carry a lot of stress at 1,000. So we are limited in our materials to most often less than 530 degrees Celsius, 528 strictly, because that happens to be 1,000 degrees Fahrenheit. We mostly, mechanical engineers will not want to go hotter than that with the material. The gas around the material might be hotter, but the material itself has a temperature limitation. Okay. So I have a bit of background in pressure exergy, and these two images are from ages ago. These are from 2008, I think, maybe 2009, when I was very interested in storing air underwater. And the reason for doing that is that you can store pressure exergy in the air underwater. So I did two things. I made some kind of small scale balloons, which I put in a water tank, and I inflated them and deflated them innumerable times in Nottingham to find out exactly what I expected to find out. Nothing happens. Nothing interesting, nothing bad happens. You can inflate and deflate a balloon many, many hundreds of times without it ever having any problem. And then I got a much bigger balloon. This is 40 cubic meters of balloon, and I put that underwater in Scapa Flow, off the side of a workboat and then down underwater. And that got noticed by quite a lot of people, actually. It was regarded as a radical idea in its time, although lots of people kind of independently invented that same idea. But the key point is this: if you have some background in storing pressure exergy, and particularly with compressed air energy storage, you realize something very, very interesting. And this is a slide that's taken from a talk that I gave in January 2019, which was at the Brian Lavelle meeting at the Geological Society of London. I was explaining compressed air to people who actually don't understand compressed air. And that's most of the world, by the way. Almost nobody understands compressed air energy storage properly. But here's an interesting thing. If you take a volume of air and you expend 100 joules of work to compress that air, and then you allow the air to come back to its original temperature, the amount of heat that comes out of that air is 100 joules. No matter what. It doesn't matter how efficient the compressor is, it doesn't depend on anything. You expend 100 joules of input work to compress some air, and I guarantee you exactly 100 joules of heat will come out of that. So if you stand back from that and you think about it, well, I put 100 joules of work into the air, and then 100 joules of heat fell out of the air. So the total increase in energy in that body of air is 0. And so that's a very disturbing thought, because you think, well, I can't possibly have wasted all that effort just to put 0 energy into the air. But the fact is, you have put 0 energy into that body of air. You have simply put in some exergy. And if you managed to compress that air completely isothermally, so in other words, all the heat that fell out whilst you were doing the compression was exactly at ambient pressure, then you would have put in exactly 100 joules of exergy, and you could get that back out. Right, that stuff is background. We can come back to that. This is about hydrogen, what we're talking about today. And hydrogen is a fantastic fuel. It has a very high calorific value, which is to say, if you set fire to a kilogram of hydrogen, it will release approximately 142 megajoules of energy. That's fantastic. It's about 3 times as much as kerosene. So absolutely more than 3 times as much as kerosene, not quite 3 times as much as methane. So that's a fantastic calorific value. It means that if you carry a kilogram of hydrogen around with you, you can release a lot of energy, but there are limitations on that. And the first limitation is something I mentioned earlier on, is this business that we can't allow that hydrogen to go up to 2000 degrees, not because it isn't possible to do that. It is possible to do that. But if you've got the hydrogen or combustion products at 2000 degrees, you can't actually make a machine that will take the energy out of it. So because of limitations with the machines, we have a realistic minimum of about half of that much. Well, in fact, people talk about half, about 50% of the lower calorific value. This is the upper calorific value, details. But in broad terms, you can expect to get about 60 megajoules per kilogram of work just from the chemical potential of hydrogen. So that's still pretty good. I mean, that's 60 megajoules per kilogram is more than the calorific value of kerosene, which is about 45. However, hydrogen has a problem, and in some ways it's a problem, in some ways it's a good thing. Hydrogen is very light, and that makes it inconvenient to carry it around or to store it because it has low density. So whilst you can get a lot of megajoules into every kilogram of hydrogen, you can't get a lot of megajoules into a cubic meter of hydrogen. And in fact, for the same pressure, methane stores about 3 times as much heat energy as hydrogen. And that's kind of interesting. If you have caverns for storing energy, and you think about, should I put methane or hydrogen in them? Well, if you were only interested in how much energy can it release, methane's your man. So because hydrogen has a low density, then if we want to store it, we want to do usually one of 3 things. We either use high pressure to store hydrogen, and it's not unusual for hydrogen to be stored at 700 bar, that's 700 times atmospheric pressure. Or we can liquefy hydrogen and store it at very, very low temperatures, but that's incredibly low. That's 20 Kelvin, or around about 20 Kelvin. So it's very, very cold, that. Or we can attempt to use some kind of adsorption process, or literally store hydrogen in something like ammonia, and then get it back out again. So chemical or physical bonding to store it. So this is the key point of my talk. For hydrogen in particular, the temperature or pressure exergy content is never negligible. And for other fuels, it is pretty negligible. When you fill up your car with petrol, if you still have one of those, or diesel, the amount of energy that it takes, the amount of work it takes for the pump to push the diesel into your car is so small compared to the energy content of the diesel that nobody even does a calculation on it. It's just so incredibly small. It's far less than 1%. And with hydrogen, that is not the case, and that fact is important. So how big is pressure exergy then? And here's a formula. It's the only formula in the presentation. This tells you how much exergy, mechanical work, you can store in a container that has a volume V1 if atmospheric pressure is P subscript 0 and R is the pressure ratio. So it's P0 atmospheric pressure multiplied by V, the volume of the stuff that you're storing, and multiplied by R log R, take away R minus 1. In very crude terms, the R log R is the amount of work that gas would do if you expanded it all the way back to atmospheric pressure. So that's the work that you can get out just by expanding it back slowly. And I say slowly because you have to let heat come into the gas as you're expanding it. And the second part is a tax that the atmosphere takes off you, because as you expand your original gas, you have to push the atmosphere out of the way, and so that's a tax. And atmosphere takes this much tax. So here's an example: 1 cubic meter of hydrogen at 150 bar, is very tame pressure, has about 13 kilograms of hydrogen in it. And so the content, the amount of work you could expect to get out of burning that is about 780 megajoules. And the pressure exergy that's in it is 60. So not quite 10%, but not far off 10%. So it's not negligible. And you might not be impressed by that, but then you have to think about something additional, which is, what reference temperature are we talking about? When we define exergy, we're talking about the amount of work that we can release by bringing something back into equilibrium with, let's call it a reference temperature. And usually the reference temperature is the ambient temperature. Usually it's the temperature of the air around us. However, in the case of hydrogen, whenever we are going to use it, when we're going to oxidize it somehow, we're always going to have an abundant supply of waste heat. So for example, if you're going to put hydrogen into an engine, you're going to burn it inside the engine, and the engine will get hot, and the engine is only about 50% efficient. So about half of the energy that was in the hydrogen is going to drop off as heat. So there's loads of heat available whenever you're burning hydrogen. And so the temperature that you have for expanding this hydrogen might be much higher than just atmospheric temperature. It could be 3 times higher. 3 times atmospheric temperature would be a little bit over 540, let's say 600 degrees Celsius. Very, very sensible temperature for us to get work out of a gas. So probably a realistic estimate of the pressure exergy available in that 1 meter cube of hydrogen at 150 bar is more like 180 megajoules. And that is almost a quarter of the work available from the chemical exergy alone. Okay, so most people ignore this. And I gave a report, I gave a seminar in 2022. So, oh, look, almost exactly 2 years ago, I gave a seminar primarily aimed at Rolls-Royce, but it was also aimed at the Aerospace Technologies Institute, because people keep on ignoring this very large amount of exergy that exists in hydrogen, particularly, by the way, in liquid hydrogen. That's much more rich because of how very cold the liquid hydrogen is. There's gold dust of exergy in that coldness. So here's a report by McKinsey, who got it completely wrong, despite their high reputation for getting things right. And here's a report by the ATI from 2022 that also got it completely wrong, because they both calculated only the chemical exergy in hydrogen. Nearly finished. How do you release that exergy? Well, here's an idea that I thought I had. At least I thought I was the inventor of this, and this goes back to April 2021. Over here is your tank of pressurized hydrogen. You let high pressure hydrogen come out of this tank in a tube, and you wrap that tube around your engine. So now the hydrogen comes out at ambient temperature. Now you warm the hydrogen up to, let's say, 550 degrees, and you put it into a first expander to drop the pressure of the hydrogen down. Pressure drops in the hydrogen, and the temperature also drops. Send the hydrogen back to the engine to pick up some more heat, send it into another expander, the pressure drops some more and the temperature drops again. And then finally, let the hydrogen into the engine and burn it. And so these things can take out some mechanical work for you. So sadly, I was not the original inventor of that. Somebody had stolen that idea by a mere 10 years. And final slide before my conclusion, some people are very negative and some people are very bad engineers. And following the publication of the Royal Society report, what I would describe as the GWPF cabal, the GWPF stands for Global Warming Policy Foundation, decided they would criticize that report. And a few of them got at it, but one commentator in particular was especially daft. And that was Mr. Turber, because he had a go at energy returned over energy invested. And he got just about everything a guy could get wrong. This is his blog, but he refers to it, a schematic that was published by the Hydrogen H21 group that also neglected the physical exergy of hydrogen. And in fact, this diagram shows you that they more or less thought that was a nuisance, that when hydrogen comes out of a cavern, you have to, this is not true, they thought you have to throttle it to reduce the pressure. And when you throttle it, it gets warmer, oddly enough, as a negative Joule-Thomson coefficient. And so you have to cool it after you've throttled it. Utter bunkum, complete nonsense. So here are my conclusions. First one, storing large amounts of pressurized hydrogen will be really key for net zero UK, and we'll need salt caverns to do that, and there'll be many, many of them. Really, really important. Second point, the mechanical work that it takes to push hydrogen into those caverns is quite significant relative to the chemical exergy, and it's in the order of 7.5%-ish. And if we think about it properly, we can and we should get that work back. It's not gone. We can have it back. And in fact, we can have it back with a bonus, because if we use the waste heat, we can get about twice as much work back as we put in. And then my final bullet point is, don't believe what clowns tell you. And before I leave it, let me remind you that that is the link for the conference, and we can still accept a few more registrations. Thanks very much.
Thank you very much, Seamus. It's a very nice presentation. Yeah, so I think we can keep the questions towards the end of the webinar. So
Sure.
maybe Hossein, if you can give your presentation by sharing the screen, that would be great.
Could I just introduce, this is Goran. Can you hear me, colleagues?
Yes, Goran, hi.
Hello, Goran.
Hi, Seamus. Yes, I mean, you just to say, you gave a very strong but also negative aspects of hydrogen, and I think we want to discuss this more with you in depth. And also we have and Hossein will present, because we've got this pretty advanced model regarding the transport of hydrogen, which demonstrates that some of these energy storage and so forth can actually enable, although it's a low energy density, they can actually make it work. But anyway, I completely agree with you that it would be important to make sure that we provide some fundamental evidence, so that what are the pros and cons, so that because there is, as you said, there is a massive disagreement in the community regarding hydrogen, which we need to really get involved and provide some
completely agree. I completely agree. But if you interpreted me as being negative about hydrogen, absolutely not at all negative about hydrogen. That's a complete misstatement. But I'm just saying we think about the mechanical engineering as well.
Indeed.
Thank
Okay,
you.
sorry for this. Just that this challenge needs to be addressed. Thank you.
Thank you. So Hossein, over to you. If you can keep it 15 minutes, just to leave maybe 5 minutes for Q&A. Thank you. Thanks. Hossein, I think you're muted.
Sorry, can you hear me now?
Yeah,
yes.
You're good now. Thank you.
Oh, sorry, I was muted. I'm sorry. Yeah, I was just mentioning that this presentation will focus more on the whole system perspectives and looking for what role can bring from the whole system benefits and so forth. And that's the idea that here we are presenting here. So if I just move to the next slide, first, I'll just skip the content. First, just some hydrogen strategies from international to Europe, and then national UK strategies that they have for the hydrogen. As you can see, there are lots of countries and regions that they are having some strategies or plans, which nearly 50% of the global GDP countries have already, or they are kind of having a national hydrogen strategy to have in the future in order to reach this net zero emission targets. And in terms of the Europe, one of the main aspects is the European hydrogen backbone, which the idea here is that using the existing almost 40,000 kilometers of gas pipelines to retrofit and repurpose for hydrogen, and which 70% of them, as mentioned, with the average cost of around 10 to 20 euro cents per kilogram of hydrogen can be done in order to repurpose the existing infrastructure to transport hydrogen. And that's also one of the main focuses of this study. And in terms of the UK, in 2030, for example, we will have significant installation of offshore renewables. In 2045, we would have an NTS, a National Transition System for Hydrogen. And 2050, obviously, is the UK should achieve the net zero. That's kind of what National Grid proposes for the hydrogen roadmap until 2050. So that's the hydrogen value chain. But I think all the people here should know about this, that in terms of production, we have different ways of producing hydrogen, which in the next slide, I'll just go into a bit of more detail. And for transport, we could use different hydrogen energy carriers, such as ammonia as well, and LOHC, as well as we could use pipelines or vessels, depending on the scale of the hydrogen that we want to transport. And utilization, it can have in many different aspects we can use hydrogen. Different hydrogen production technologies, blue and green are the main ones so far, and for blue we can have SMR, ATR, which if we combine them with CCS, this makes them kind of low carbon technologies, and for green, different types of electrolyzers, and also a method of pyrolysis, which is kind of more now in the ongoing research and development, which is kind of splitting methane into hydrogen and solid carbon, which can be used for industries. In terms of different storages, in here we could have 4, let's say, main technology groups, from line pack, which is the storage within the pipelines, distributed above ground storages, which are the small capacities usually considered for daily to weekly storage, and then the salt caverns and disused oil and gas fields, which those goes to months and seasons of energy storage. So here, as just Seamus also mentioned, hydrogen has a lower density compared to natural gas, so therefore we could say we need to have more volume of hydrogen. But in the future, in the net zero energy system, it is very likely that we replace hydrogen with natural gas. So therefore, these aspects of lower density can become challenging, as well as since we would have lots of renewables in the system. So this will also will increase the variability and intermittency of the operation of the energy system. And the gas system and the electricity system are linked by hydrogen-based power plants, electrically driven compressors, and electrolyzers. So therefore, these 2 main aspects will be, let's say, make lots of challenges in the hydrogen network operation, or let's say the gas network operation as well. And therefore, here is where the line pack and the hydrogen storage facilities could play a very important role in order to maintain the security of supply. And in here, therefore, the integrated analysis of these 2 systems becomes very important in order to achieve this cost-effective transition to low-carbon future. So these are just showing the components that we kind of assume in our model, that from hydrogen production, different routes, blue, turquoise, green, and then which from the renewables, we could have either, obviously, electricity or producing green hydrogen, and then the exogeneration from different sources, nuclear, hydrogen-based plants, natural gas plants, biomass plants, CHPs, and then at the bottom we have this transport of hydrogen or electricity transmission in different levels, and obviously utilization and storage is also another components that we consider. And in the right hand side we could see that also there's an idea that we could produce hydrogen offshore. I mean, we would have lots of offshore renewable installations, and we could use the nearly 35,000 kilometers of existing natural gas pipelines which are in the North Sea. And here we have 3 configurations that could be possible. The first one is just having electricity, transmitting electricity and having electrolyzers onshore. The next is a combination of having offshore and onshore electrolyzers, which the energy would be either transmitted through electricity by transmission lines or through the gas pipelines through hydrogen. And the third one is, for example, having just only offshore electrolyzers. And the model that we use is called Integrated Hydrogen and Electricity Model IHES, which here we have just different inputs. And the objective function of this model is to minimize the total operation and planning costs of both hydrogen and electricity systems simultaneously, while meeting the future 2050 emission targets. And in this study, the case study is the GB, obviously, and in the left-hand side, you can see the gas NTS and also some offshore locations, which comes to an 85-node gas national transmission system. And in the right-hand side, we can see a simplified electricity transmission with 29 bus bars on onshore, and the rest goes to offshore, which is the location of the offshore renewables. And those blue dashed lines are actually the investment that is required on the offshore electricity transmission in order to make that happen. The case study, first of all, we will consider two different heat decarbonization pathways: the deep electrification, which is mainly based on heat pumps, but we have also a hydrogen pathway, which is mainly based on hydrogen-based boilers, which the idea is to just replace the existing natural gas boilers with hydrogen boilers. However, here we have only 2/3 of the heat demand will be based on hydrogen. The rest would be still on electrified heating, because the only customers which are connected to the gas network will be replaced with hydrogen boilers, but the rest, which do not have access to the grid, they will be electrified. And as you can see in the right-hand side, the annual demand figure, this is actually the demand in electrification pathway and in the hydrogen pathway. And on top of that, we have here two cases. First, considering not having green hydrogen supply, which therefore the supply would be mainly based on blue and BECCS, which BECCS can also provide negative emissions. BECCS and DACS is also considered in the study. And the mixed case, which is also including green for supplying the demand. And also extreme weather events is considered in order for kind of see what's the role of hydrogen in supporting the resilience. And left-hand side, we can see a windy summer day. We have, let's say, lots of renewables, but the demand is low. On the other side, in the cold winter day, we have low renewables and the demand is high. So therefore, that's where exactly the challenge would be, and how hydrogen storage and so forth could, let's say, facilitate in order to secure the supply-demand balance. So I just jumped to some results. Hydrogen supply and demand. At the top, we can see the hydrogen production technologies, the capacities. Obviously, in the no green cases, we don't have any green installation, but it can be seen that the majority, or let's say, at least in the electrification pathway, we don't need to have any more blue hydrogen. We can replace it all with green hydrogen, because the demand in hydrogen system is lower compared to the hydrogen pathway. And therefore, the combination of the BECCS, because that provides the negative emissions, and the green hydrogen supply will be sufficient. And also the hydrogen storage technologies that here we just assume very simple underground and overground, which the overgrounds will be mainly in the medium pressure, low pressure, for example, distribution networks. However, the undergrounds are mostly here based on the salt caverns that we could see the difference in different decarbonization pathways. And at the bottom figure, we can see now the energy-wise in terawatt hours per year. That's an annual kind of 2050 annual study, which is on hourly basis. However, due to the complexities, we have a demand clustering algorithm, which we choose 30 days, representative 30 days of represent the whole year. And in presence of the green hydrogen supply, the supply from the blue is reduced. That has three main reasons. First of all, we are utilizing renewables and use of the whenever we can to produce green hydrogen. Second of all, the blue hydrogen production spatial limits, because since we are using the existing gas infrastructure to inject hydrogen, so we are assuming that the blue hydrogen plants would be only near to the natural gas terminals in order to bypass the natural gas transport within the infrastructure. And then also due to the hydrogen transport issues, if you have this green, because we are optimizing the electrolyzers in the whole system, so we can have just everywhere and depending on the optimal allocation of that, and therefore we can see more also green hydrogen supply. And one of the reasons that we can see here the power, for example, here the hydrogen for power in this scenario is quite large. However, in the hydrogen pathways, it's very small. And the reason is that because we need to meet the demand for heating. And that's kind of priority, and the electricity demand is lower compared to the electrification pathway. This is the electricity supply and demand. First of all, one of the very good aspects here, if we have electrolyzers, we are significantly, the renewable curtailment is reduced up to 77 terawatt-hours per year. And then also we could have more generation of hydrogen-based gas plants if the green hydrogen is available. That gives us a bit of flexibility. And as expected, in these cases, since we have electrolyzers, the electricity demand is increasing in those. So that's also another challenge for the electricity system. And therefore, we have also some other flexibilities, such as electricity storage and demand side response and so forth to make that happen. And also more frequency response is required in these cases because we are integrating also more renewables. So that's also another aspect that needs to be considered. Now, if I just go into detail of hydrogen system operation, that's kind of the role of storage within the pipes line pack. As I mentioned, we have 30 representative days of the year. And here we are showing the line pack swing, which line pack swing is the maximum line pack available minus the minimum line pack available within a specific day. And this kind of is one criteria that shows how the system is working and how much the system is under stress and so forth. And it can be seen that in the hydrogen pathway, we can see most of the time we have higher swings on the same day. And the reason is that because obviously the hydrogen demand is higher due to the hydrogen demand for heating. So therefore the system is more under stress and the line pack should, let's say, support more the system in order to maintain the security of supply. And it can be seen that we can reach up to 74 million cubic meter per day in the hydrogen pathway, while, for example, currently in 2021, according to National Grid, for the NTS, it was around 41 million cubic meter. So that's also another challenge for the hydrogen system operator in case that injecting hydrogen compared to natural gas. However, but on the other side, hydrogen storage facilities can play a very active role and important role in order to make that happen. So as I mentioned, we also consider extreme weather events. So we want to see what's the role, how the resilience is in this case. In the mixed scenario, which we have all the options, it can be seen that in the cold winter days, in both of them, hydrogen storage are also actively providing hydrogen to the system, while in the windy summer days, we are injecting to the hydrogen storage facilities. And that's exactly where this hydrogen storage is acting very important in order to support resilience, because in the cold winter days, we don't have much of renewables. So, and since in the system 2050, we will have, the system relies highly on renewables. So this hydrogen storage facilities could kind of act as a flexibility and enhance the system resilience. And just to mention here also that if we compare the no green case with the mix, that's just the changes here. In case of no green hydrogen supply, obviously we will have more supply from the blue hydrogen because that's what we have here. And in some cases, we needed to inject more hydrogen to storages in order to support the electricity system balance, because we needed to provide the hydrogen to the, let's say, hydrogen generation, hydrogen CCGTs. And therefore we need also, actually hydrogen storage also acting as a flexibility tool to support the electricity system. And that's how that's been here presented. So I just wrap up with the key findings. First of all, hydrogen plays a crucial role in cost-effective transition, and it can have benefits in the system balancing, energy security and resilience against extreme weather events. We were able to transport hydrogen within the existing infrastructure. Let's say just replacing the hydrogen with natural gas with hydrogen in the existing NTS, which is but subject to appropriate line pack management and sufficient allocation of storages. And line pack provided this intraday flexibility to deal with this renewable intermittencies, and also that how the hydrogen storage kind of acts here as a buffer, kind of storing hydrogen in windy summer days and then withdrawal of the hydrogen from the storages in cold winter days, which the system is under stress. And that was also one of the other conclusions that we could achieve. So I think that's pretty it from my side. I hope I kept it in time. So yeah, I tried to be very quick.
Thank you very much, Hossein. Thank you. Very nice. So we have a few minutes. Perhaps I can see there's 2 questions in the chat box. So one is from Dr. Jekun Guo. So he said, I have a question for Professor Garvey. If the reports for hydrogen-powered aircraft have been wrong as they only calculated chemical exergy, is there any methods we can use to calculate correctly?
Yes, there are, and it's quite straightforward. You can put in formulae to calculate how much exergy there is in the hydrogen, and I think most people would acknowledge that that's easily possible. The big challenge is, can we design machinery that can get it back out again? That's really the challenge, and that's a challenge that I put to Rolls-Royce more than 2 years ago. I pretty much had to beg them to be allowed to give a seminar on February in 2022, and then subsequently I gave a seminar here at Nottingham in April, and that Rolls-Royce is working on that, looking at how it can make machines that can recover some of that. But you can put in numbers into the formulae, and it's quite staggering. It's about a third again is available to get if you have the right machines. So if you calculate only the chemical content, you are underestimating by about 1/3.
Thank you, Seamus. So there's another question, which is again for Seamus. So let me see. So would H2 exergy concept be applicable to H2 storage systems on board for HGVs or buses that use fuel cells and 350/700 bar tanks? If yes,
yes, absolutely. 700 bar tanks we prefer because there's more exergy per kilogram of hydrogen in the 700 bar tanks. And the key thing about fuel cells is there are different types of them. The solid oxide fuel cells run very hot, and they're fantastic for this purpose. The PEM run very cold, and they're no good at all for this purpose. So if you want to get back the best value you can out of hydrogen stored at pressure, you really have a very strong motivation to go towards solid oxide fuel cells.
Okay, thank you, Seamus. So maybe we can have one more question. So maybe Hossein, you might be the person to answer this. So how do you see the future landscape of energy storage have both batteries and hydrogen? Any common areas?
Well, from my perspective, we can have both because more or less batteries, let's say up to probably daily, weekly storage that we could have. However, from the other side, seasonal storage. So I don't think these two interfere, but these two will definitely complement each other, and we could have that's an area that both can be in place from my perspective. I hope that I answered properly the question.
Okay, yeah, thank you, Hossein. So because of the interest of time, I think we will conclude the webinar here. But again, thank you very much for Seamus and also Hossein for the presentations. And I want to thank Tong, who co-organized this webinar with me, and also the support from HI-ACT and also Supergen Energy Storage Networks Hub. And again, of course, thank you for everyone to attend. And I hope you will find this session informative. And do please feel free to reach out to Hossein and Seamus if you have any more questions by email. I'm sure they'd be very delighted to respond to you. So thank you very much and have a nice afternoon and take care and thanks again. Cheers. Bye-bye.
Thank you. Thank you all.
Thank you.
Thank you.
Cheers.
Thank you, everyone.
Thank you.